Okay, so we're going to be looking at 5.2 today, and 5.2 is bisectors in triangles. And today we're going to be looking at a bunch of theorems. We're going to be looking at theorem 5.2, 5.3, 5.4, and 5.5. We're going to be talking about perpendicular bisectors, and we're going to be talking about angle bisectors. And then once we've done all of that, then we're going to be using a bit of algebra to find the distance from a point to a line. Oops. Alright, here we go. So for starters, let's go ahead and look at a perpendicular bisector. Get ourselves set up here. So if we happen to look at a line and its perpendicular bisector, and we can call this line AB, and the perpendicular line CD. If we know that this is a perpendicular bisector of AB, bisect means to cut in half. And so we know that these two legs are going to be the same size. And we'll go ahead and label that intersection E. So if we have a perpendicular bisector, we know that DC is at 90 degrees to AB. Here's the other neat thing. If we have a point on DC, because AE is the exact same thing as EB, or they are congruent, we know that the distance from A to D is going to be exactly the same as the distance from D to B. And this will work no matter where this point is along this line DC. All of these are going to be the same distance, or equidistant. We'll go ahead and label this one over here in the left-hand column. Alright, so let's hit theorem 5.2. Theorem 5.2 is pretty close to what we just described in our perpendicular bisectors, and theorem 5.2 is in fact the perpendicular bisector theorem. And it's just generally a formalized version of the diagram that's up there. And it says that if a point is on the perpendicular bisector, oh goodness, of a segment, then it's the same distance or equidistant from both endpoints of the segment. And basically what this is doing is this is just kind of reiterating what's going on up here in the diagram. So if we're looking at, again, AB, all it's saying is that if DC is the perpendicular bisector of AB, any point, whether it's point D, whether it's one of these lower points, they're all going to be the same distance from A and B. That's all it means. And so next up, we're going to hit theorem 5.3. Now a lot of these theorems in chapter 5 are going to come as pairs. And they're going to come as pairs because most of them are just converses. So converse, remember, is just the same thing as the opposite. And so I'm going to go ahead and box this to kind of set it apart. This is going to be the converse, and not like the shoe, converse of the perpendicular bisector theorem. Great. And this just means that if a point is the same distance from the endpoints of a segment, comma, then it's on the perpendicular bisector of the segment. So what does this one mean? Well, this just means if there's some point and it's the same distance from two endpoints, it's on the perpendicular bisector. Converse, opposite, or backwards. This is the point at which you should take 10 seconds and stand up, stretch, say hi to your neighbor, and turn around in circles 3 times. And if you finish that already, then I have a bridge that I'll sell you. Now, well, let's do an example. How about? We'll call this example A. Now, if we have a diagram that looks a little bit like this, and we know that that's a right angle, and we know that those are the same, trust me, and that this has a side length of 5, and that this has a side length of 6. What we want to do is we want to decide if we want to decide first off if there are any perpendicular bisectors. Then we want to know the measure of AC and the measure of DB. So first let's look at this. We have two perpendicular lines, right? AB and CD, or two perpendicular segments. We look at AB and we can tell from our little congruency tick marks here that the distance between A to CD and the distance from B to CD is the same. And so we know that this line is being bisected or cut in half. And since CD is at a right angle, we know that CD is the perpendicular bisector of AB. So the answer to our first question is naturally yes. Now we also want to know the measure of AC, or this guy here, and we want to know the measure of DB. Well, we can use theorems 5.2 and 5.3 to figure this out pretty quick. Now remember, 5.2 and 5.3 tell us that if we have a point on a perpendicular bisector, it's the same distance to both endpoints. So since the distance from C to B is 5, A to C has to be 5. And since the distance from A to D is 6, D to B has to be 6 as well. If you're looking at this and thinking, well, that looks too easy, it really isn't. It's just this easy. It's not too easy, it is this easy. So don't make it harder than you need to. Let's hit a definition real quick, and then we'll get to the last two theorems, and then one more example, and we'll be done. Now, the vocab term that I'm going to throw at you really quick is definitely a term, and it's going to seem pretty self-evident because it's pretty easy to understand. It's the distance from a point to a line. And this is really just as simple as it seems. If we take a set of angles like this, if we've got A and B, C, and D, if we have a perpendicular segment from B to C, and we have a perpendicular segment from this point, or this little area on AD to AC, we can find that these two lines are the same thing. And what this hinges on is both of these perpendicular lines passing through the same point. So again, we need a perpendicular line here and a perpendicular line here. That was probably a terrible definition. There's a really good one on page 250 in your book. It's kind of wordy, but if you really want to read math at 10 to 1 in the morning, then feel free. Moving on. Theorems 5.4 and 5.5. Theorem 5.4 is the angle bisector theorem. This is going to be really easy. if a point on the bisector or if a point is on the bisector of an angle, then the point is the same distance from the sides of the angle. Now, this works with our diagram here, and it can work in two different ways. So, if we have a point, letter E, and it's on the angle bisector of angle BAD, here's the deal. E is the same distance to AD as it is to AB. Now this works only if we have two right angles. And the right angles can be on the exterior rays, AB and AD, or they can be on the interior ray, like this. If this is a true angle bisector, AC, if it's a true angle bisector, point E is the exact same distance from both of the exterior rays. That's really all 5,4 is saying. 5,5, like I said earlier, is going to be the other half of this pair of theorems. And it's the converse of the angle bisector theorem. And this is going to be pretty much the exact opposite. So if a point in the interior of an angle is equidistant to both exterior rays or to both sides, of the angle, it's on the angle bisector. So again, back to our diagram. Let's just say that we've got a point E, and it's the same distance to AD as it is to AB. If that really is the same distance, then it's on the angle bisector. Has to be the same distance to be on the angle bisector, has to be on the angle bisector to be the same distance. Alright, last example. Example Roman numeral 2. This one, we're going to be using the angle bisector theorem. And we're going to look at another diagram as promised. Trust me, these lines are straight. Now, we're going to assume that we'll say FDA is bisected by FBI, and we can label this one FED and this one as FSA. We're going to assume that SB is at a right angle to FA and EB is at a right angle to FD. Now, we're also going to tell you that SB has a side length of 5x, and we're also going to tell you that BE has a side length of 2x plus 24. Now, without looking at anything else, let's think about this whole diagram. We can tell that FBI is the bisector of AFD. How do we know that? Well, we know that it's the bisector because we're told that these two angles are congruent. And if those two angles are congruent, and B is a point on the angle bisector, we know that BE has to be congruent to BS. Now that we know that both of those are the same thing, we'll just use some algebra. And since we know that 5x is the same thing as 2x plus 24, we now have an equation that we can solve really quickly. Not minus 3x minus 2x. We get 3x equals 24. Divide both sides by 3, and we get x equals 8. Now, we're not done yet, because all we know right now is that x equals 8. We still don't know what the side lengths are. So what we can do is we can plug 8 back into our original equation or into both terms here and figure this out. So let's do SB to start with. 5 times 8, somebody quick, 40, thank you. And on the other side, 2 times 8 plus 24. 2 times 8 is 16 plus 24. We get 40. We know that BE has to be the same as BS. We see that they are both indeed 40. And we are correct. All right. Finish this thing off. So we talked about really a couple of theorems today. 5.2 and 5.3 are the same thing. They're just converses of the other. And 5.4 and 5.5 are really the same thing, but they're just converses again. And so we talked about perpendicular bisectors. And we talked about angle bisectors. That's what we did today. That's it. That's it. That's all we did. And so, to finish this off, why don't you take care of the assignment that's on the board, but I'll also put it here. You should be on page 252, 12 through 15, 18 through 25, 28 through 30, and 41 and 42. All right. If you're watching this, that means I'm not back yet, and so hang on to your assignment. You're going to get an extra day, and if you're not watching this, then it doesn't matter. Thanks.